Hi, I want to take a quick moment to go through my derivation for the divergence in polar so that you have a chance to see how it and the curl in polar, which is a very similar conversion, work out with the dot product, not in terms of how we normally use the shorthand of comparing components in vectors or in a matrix, but in terms of the fundamental definitions of how vectors dot together. So a quick overview of it is that we're going to focus on how r hat and theta hat relate together. So let me just show you the work as a whole, and then we're going to erase it and go through it again. We start out with two pieces. The del operator in polar, which has a radial component and angular component, and the general field in polar. So now we're going to combine these two pieces together using the dot product in its fundamental form of how the vector directions dot to either 0 or dot to 1, because these are orthogonal directions, r hat and theta hat. But before we can do that, we need to take the r partial of the whole right-hand side and the theta partial of the whole right-hand side before dotting with their respective directions. So before we dot with r hat, we need to take the r partial of both pieces. Now to do that, we need to remember that r hat can be written as cosine of theta, sine of theta, which means it does not change with r. It's constant in terms of the radial distance. Its direction is the same direction regardless of how far out you are. Theta hat also is constant. The direction is constant with respect to r. Doesn't matter how far out you are, the direction it points is always the same. So when we take the derivative in terms of r, the partial derivative, m, function of r and theta, goes to m sub r. R hat is like a constant direction we multiply by. Then we have n over r, and n is a placeholder for some theta partial derivative of my surface function, but it can be a function of r and theta. So we get a product rule, n sub r divided by r, taking derivative of the n first, and then subtracting n over r squared. Now you could use a quotient rule, but this is just fun. Times theta hat, because theta hat, again, is constant with respect to r. Then we add the dot product with theta hat. So we're going to first take the derivative in terms of theta and then divide by r. So working backwards, I'm going to multiply by 1 over r after I've taken the theta partial of each piece. So let me go through and take the theta partial of r hat and theta hat separately. I get a negative sine of theta and a cosine of theta, which is theta hat direction. So the derivative of r hat is theta hat in terms of the angle. But what about the derivative of the angular direction as we change in terms of the angle? Notice this is the vector and this is a scalar, so it's not 1 necessarily. So we look at this function, take the derivative, a negative sine goes to negative cosine, cosine goes to negative sine, and we can factor a negative out to get a negative r hat as my derivative. And so that leaves us with a product rule here. M sub theta r hat, where we take the derivative of m first, plus m times the derivative of r theta, theta hat. And then we take the theta derivative of n over r times theta hat. That gives us n sub theta over r times theta hat. And then plus n over r times r hat. That's negated, isn't it? So again, since r hat and theta hat are functions of theta, we need to treat these two as product rules in terms of theta, the theta derivative. Now that we've expanded out the derivative, we've done that first, we can then divide by r here and dot with our respective directions. So let me just remember how these directions work. R hat dotted with theta hat is 0 because those are orthogonal, but r hat dotted with itself is equal to the magnitude of that vector squared. But since it's a unit vector, that's just 1. And the same thing's true for theta hat dotted with theta hat equals 1 as well. And so let's first look for all the zeros. R hat dotted with this whole piece, r hat will dot to 0. And then theta hat dotted with this r hat piece, that will go to 0. And that r hat piece will go to 0, leaving us with m sub r from r hat dotted with itself, plus m over r, theta hat dotted with itself, plus n sub theta over r over r squared, theta hat dotted with itself. And that gives us the divergence of a vector field in polar coordinates. And again, m and n are general placeholders for the r partial and the theta partial of your surface, which means you can use the same formula to compute the Laplacian of P, del dotted with del P. Okay, that should be enough to make sure you check your work on the divergence, do the same process for the curl, and then use this result for the Laplacian.